Hi, I'm Tashen Pakrisami, and I'll be going through our research in the field of crowd density estimation. This research was conducted at the University of Witwatersrand and was supervised by Dr. Richard Klein. We focus on the ability of dilated convolution to capture scale-invariant context in the field of crowd density estimation. So the formulation of the CDE problem can be described as a mapping from an image of a crowd, as you can see on the left, to a density map that describes the spatial distribution of density in the given crowd image. If you look at the input crowd image, we can see that the crowd is highly congested at the top of the image, and you can see that the density map corresponds. So once we have the density map, the final step is to predict an overall crowd count. This is basically just the number of people present in the crowd image. The count is commonly found by simply summing the values of the density map. So what is this technology actually useful for? It is known that managing crowds can be very difficult at a large scale, and poorly managed crowds can lead to injuries or death. CDE could make it easier to manage crowds, as safety officials would have a clear idea of the formation of a crowd and where the density might be reaching a dangerous level. This could help to prevent issues like stampedes in dense crowds. CDE also could be used to analyze the movements of mass commuters and allow developers to build infrastructure that fits the observed movement. This could therefore increase efficiency and safety. In addition to that, it could be used to automatically count crowds, possibly to measure the turnout or attendance of an event. We could use this attendance count to make sure the attendance doesn't surpass the maximum capacity of a venue. Some of the common challenges in CDE include occlusion and scale variations. Occlusion refers to when an object cannot be recognized by the sensors used to feed the algorithm. In this case, the problem is that many people overlap and block others, as you can see in this photo. There are also often large variations of scale between people in separate crowd images as well as within single crowd images. As you can see in the image, the people closest to the camera appear much larger than those far away. We therefore need to try address the problem in a scale-invariant way. The two most important concepts needed to understand this research are dilated convolution and a true spatial permanent pooling. Dilated convolution refers to when a kernel's receptive field is spread out without increasing the number of parameters. This is done by skipping positions when defining a kernel, and an illustration of this can be seen on the left. This larger receptive field captures more context but does not increase the computational cost. The dilation rate refers to the amount the kernel is spread out by dilation, and a dilation rate of 1 is equivalent to traditional convolution. A true spatial permanent pooling applies multiple dilated convolutions with different dilation rates and therefore different receptive fields. The features from these convolutions are concatenated to create a multi-scale feature. This layer can increase the scale invariance of the network. In our approach, we create 3 different end-to-end convolutional neural networks, or CNNs for short, and train them on the same data. These methods are then evaluated and compared. Each model's early layers are made up of the first 7 layers of a pre-trained VGG16 to reduce training time. Each model adapts the baseline architecture shown in the image at the bottom. The first model is a CNN without dilation, which we call the baseline model. The second model is a CNN with a dilation rate of 2, which captures more contextual information. We call this model the dilated model. The last model adapts the dilated model and adds in a true spatial pyramid pooling layer between the VGG output and the dilatable layers. This model is called the ASPP model and should capture multi-scale features. Now looking at the particulars of training. For our training set, we use a combination of images from the pre-segmented training sets found in the Shanghai Tech dataset. Then, for data augmentation, we apply random crop and random horizontal flips to increase the generalizability since the dataset is relatively small. The training loss that we use computes the Euclidean distance between predicted map and true map, and this therefore forces the model to optimize for the overall density map rather than a crowd count. For evaluation, the standard mean average error and mean squared error metrics are used. The models are tested on the Shanghai Tech Part A, Shanghai Tech Part B, and UCF CC50 datasets. Each architecture is trained 10 times to ensure statistical significance. The distribution of their MSE values and MAE values can be found in the box plots. We can see that there is no significant difference between the models on the Shanghai Tech Part B dataset, but there is on the others. The mean results can be found in the table below. It is evident that the ASPP model performs best in most cases. Here we can see some of the predicted density maps by each model, as well as the predicted crowd counts in brackets. In analyzing the results, we find that the performance on Shanghai Tech Part B is unaffected by dilation. This may be due to the sparse data and relative lack of scale variation in Part B. We also find that the dilated model performs better than the baseline on high-density datasets. This may be due to the fact that the larger receptive field captures more contextual information, making it more resistant to occlusion. Lastly, we find that the ASPP model outperforms the dilated model on high-density datasets. This is likely due to the fact that the ASPP layer captures multi-scale features, which leads to a level of scale invariance. In conclusion, we framed the CDE problem, and subsequently through comparison of the three architectures, we evaluated the impacts of dilated convolution and found that the best approach to CDE on congested crowd images is by using a CNN of dilated kernels in conjunction with an ASPP layer to account for scale variations.